Let us start the topic called conformational isomerism. Conformational isomerism. This is the part of stereoisomerism. When we talk about the stereoisomers, these are the different structures or compounds which differ from each other, not in the structure, that is, they have the same linking of atoms, but they have different relative position in space. Those are termed as stereoisomers. So when we talk about the stereoisomers, these are the different compounds or different structures of the same molecule in which the atoms have the same linking, but they differ from each other in the relative position in space. That's what we term as stereoisomerism. Now, before we talk about conformations or conformational isomers or conformers or skew isomers or torsional isomers, let us understand a very important and a simple concept called a molecular plane. When we talk about the molecular plane is a plane. We need to understand that a unique plane can be defined by joining any three non-linear points. We always say that the 3 points, non-linear points, are always in a plane. So when we talk about a molecular plane is formed by joining any three non-linear atoms in a molecule. These atoms do not need to be attached to each other. They might be any atoms in the molecule. That will define a molecular plane. Now let us consider a simple example. Let us say we talk about an example of ethene. When we talk about ethene, ethene has this structure. Now here we have all the atoms to be non-linear. Whatever three atoms we talk about, those three atoms are not going to be in the single line. That is, they are non-linear. So that would mean that we can take the combination of any three atoms and we are going to get a plane. For example, let us consider this hydrogen, and this carbon. Now that will define a plane. Then we can talk about this hydrogen, and this carbon. Again, it defines a plane. We can have this hydrogen, this carbon, and the hydrogen. That also will define the plane. Then we could have this hydrogen, this carbon, and this hydrogen. That also will define a plane. Or we could have something like these carbon, this hydrogen, and this. We can have the same plane. So we can have any number of planes. So all these are going to be the molecular planes. We can even have this hydrogen, this carbon, and this hydrogen. That also will define a plane. What we can understand here that although we have been able to define multiple planes, but these all planes coincide. That is, we are actually defining a single plane. If we define any three atoms, we take any three atoms and define a plane, we find all the other atoms also are contained in the same plane. Effectively, we have only one plane defined for ethene. A molecule in which only one molecular plane can be defined, or a molecule which has only a single molecular plane, is termed as a planar molecule. Planar molecule. So, ethene is a planar molecule. It's a two-dimensional molecule. I hope we have understood what the meaning of the molecular plane is. Now let's talk about another example. Let's talk about a simple hydrocarbon, the simplest hydrocarbon for that matter. And the simplest hydrocarbon, here we are using this particular hydrocarbon, we are using the wedge dash structure. This hydrocarbon is called methane. Now in case of methane also, we can have the multiple molecular planes. Here again we find that any three atoms are non-linear. So we can use any three atoms and we can define a molecular plane. Could you please tell me how many molecular planes will you be able to define here? Now again, we can use a mathematical formula. Out of all the given atoms, we need to take any three atoms because all the atoms are non-linear, all three atoms are non-linear. That is why we can take the combination of any three atoms and that will define a unique plane. So, using a formula, the formula is going to be simply NC3. That is, out of the total number of atoms, we can take any three atoms and that will be defining a plane. So here, in total, this particular molecule has five atoms. So it is 5 factorial divided by 5 minus 3 factorial into 3 factorial. So that is what we have as a formula. NCR, we have already discussed this particular formula. This turns out to be 5 into 4 into 3 into 2 into 1 divided by 5 into 4 multiplied by 3 into 2 into 1. Oh, I'm just using a wrong formula. Here it will turn out to be 2 factorial, not 5 minus 4 factorial. It is going to be 2 factorial, which will turn out to be 2 into 1 into 3 into 2 into 1. So let's cancel it out. This 3 into 2 into 1 and 3 into 2 into 1 gets cancelled out. 2 gets cancelled out. 4 gets cancelled out here too. So 5 multiplied by 2 turns out to be 10. So this particular molecule is actually going to have 10 molecular planes. Now that becomes a kind of a confusing. How do we get 10 molecular planes? Now the answer is quite simple. Let us have a numbering for the various atoms. Let's say hydrogen are identical. So let's have certain numbering for hydrogens. Let's say this is the hydrogen number 1, this is the hydrogen number 2, this is the hydrogen number 3, this is the hydrogen number 4. So what we can have, initially we can talk about only the hydrogens. We can have a plane defined as 1, 2, 3. That's going to be one plane. Then we could have 1, 2, 4. That's going to be another plane. Then we have 1, 3, 4. And another one is 2, 3, 4. So there are four planes which can be defined by using only the hydrogens. And these hydrogens, they are at the periphery, that is, they are surrounding the carbon. If we join the hydrogen to form the planes, then in that case, this entire molecule is going to be enclosed in four planes, and all these planes turn out to be equilateral triangle. If a structure is enclosed within equilateral triangles, then that particular structure is termed as a polyhedron. And this particular polyhedron has four planes enclosing it. So this particular structure becomes a tetrahedron. This is the reason why we call the methane molecule as a tetrahedron. But we do have certain other molecular planes also. We could have one hydrogen, number one hydrogen, carbon, and the second hydrogen. This also would be a molecular plane. We could have one hydrogen, carbon, and the three hydrogen, one hydrogen, carbon, and the four hydrogen. We could have a two hydrogen, carbon, and the three hydrogen. We can have three hydrogen, carbon, and the four. We could have two C and four. So all these combinations are possible, and there are six other planes which are going to have the molecular planes. These could be termed as a molecular plane. So here we can find that methane molecule actually has 10 molecular planes. We can use it by the formula. We can do it by actually drawing the molecular planes. Now, if we take any two molecular planes for that matter, let's say we consider these two molecular planes. We have this particular molecular plane and we have this particular molecular plane. Now, these molecular planes are going to have a certain angle between them. The angle between any two molecular planes in the molecule is termed as a dihedral angle. This is a dihedral angle. Now, what is dihedral angle? The angle between any two molecular planes in a molecule. Now, let's consider another example. Let's take an example of hydrogen peroxide. If we consider the example of hydrogen peroxide, it has the four atoms, and these four atoms are also not linear. So the four atoms of hydrogen peroxide are not linear. Now, if they are not linear, then in that case, again, we are capable of defining the molecular planes using any three atoms. Hydrogen peroxide is easily drawn like this. Here oxygen has two lone pairs with it. So that is why the bond is not going to be linear. There are going to be two lone pairs of oxygen. Now, hydrogen peroxide actually doesn't exist mainly in this structure, but let's say we have one of the structure of hydrogen peroxide to be this. If we take the molecular plane, we can consider this hydrogen, this oxygen, the hydrogen and oxygen, and this. Now, this is going to define a molecular plane. So, this is one molecular plane of hydrogen peroxide. We can define another molecular plane. Now, that another molecular plane could be this hydrogen, oxygen, this hydrogen, oxygen, and this hydrogen, oxygen. So, this is another molecular plane. In this particular configuration, in this particular arrangement, if we see the angle between the molecular plane turns out to be 0 degrees. There is no angle between the molecular plane to coincide, and in this structure, this way, hydrogen peroxide is a planar molecule. Now let us say we hold this particular hydrogen and we pull this hydrogen towards ourselves. If we hold one particular hydrogen and pull the other hydrogen towards ourselves, then in that case, the structure deforms and we get, here we have the hydrogen, the oxygen, this oxygen. They are still in the same plane, but now this particular hydrogen which we have pulled is going to shift out of the plane. Now this structure and this structure, they will differ from each other in the angle between the molecular planes. Or we can simply say that they differ from each other in the dihedral angle. Here there is a difference between dihedral angle because hydrogen peroxide molecule can be rotated across a single bond, which leads to a change in the dihedral angle. Now these structures of hydrogen peroxide, which differ from each other only in a dihedral angle due to the rotation or a free rotation across a single bond, are termed as conformers, conformations, conformational isomers, skew isomer, or torsional isomers. Hydrogen peroxide is the simplest molecule capable of showing conformations. Now, one thing we need to understand that if we talk about hydrogen peroxide's conformations, the energy required to convert one conformation into another is extremely small. In fact, it is so small that if we try to separate the various conformers of hydrogen peroxide, then the energy that we need to supply to separate the conformers is more than enough to convert one conformer into another. So it means these conformers rapidly keep converting into each other, and any effort to separate them would lead to getting just the mixture of conformers only. For any two species to be separated, they must have stability or the energy difference more than the energy required to separate them. This energy which must be the energy difference which must be there between the structures so as to allow the separation is termed as resolution energy. If the energy of separation is more than this resolution energy or the energy of conversion from one to another, the mixture cannot be resolved. Conformers, hence, can not be resolved, they cannot be separated, and this is the reason why the conformers are not considered true isomers. Whenever you are asked to give the total number of isomers of a particular compound, you never ever count the conformers in it. You always count the other isomers, but not the conformers. Now let's consider a simple organic molecule. And the organic molecule that we consider is C2H6, that is ethane. Now let's make the ethane molecule in the Newman projection. That is, we have this particular ethane molecule. Here it's the front carbon. This is the hydrogen here. So this is what we have as the carbon. So this is what we have as the front carbon in the ethane molecule. Now, let's make the hydrogens behind. Here we have one hydrogen. Here we have another hydrogen. Here we have another hydrogen. Now, we can even consider the ethane molecule in the wedge dash structure to be this. We have the carbon here. We have the carbon here. Here we have it. This is one hydrogen. This is another hydrogen. So these are the hydrogens. Here we have one hydrogen. The another hydrogen is here. And another hydrogen is here. So the structure that I have actually made is this particular structure in which the hydrogens are actually behind each other. They are eclipsing each other. So this is the eclipsed structure of ethane. Now considering this particular eclipse structure, this is what we call as the eclipsed structure. Now what we can do is we can simply pull a particular hydrogen towards us. Now let's say we pull this particular hydrogen towards us. If we are going to pull the particular hydrogen towards us, then this hydrogen is going to move out of the plane, while this hydrogen is going to move in the plane. This hydrogen is going to move back. So the structure what we get is, so turning it a little, maybe we turn the hydrogen by something like 60 degrees. What we get is that this particular carbon, the hydrogen remain the same, but the other carbon, the hydrogen, their relative position changes. This hydrogen which was on the top actually moves out of the plane. The hydrogen which was behind, it still is behind, but it moves a little up. And the hydrogen which was out of the plane, it actually goes in the plane. So this becomes the structure of ethane due to its shift. If we are to represent it in the Newman projection, then conversion by 60 degrees would give us the same structure, but now the back hydrogens, they are going to be here. Now this particular structure is termed as staggered. Further, rotation by 60 degrees, that is now total rotation becomes 120 degrees. We end up with the first structure. That is, here we get hydrogen here, the other hydrogen here, other hydrogen here. So we end up with the same eclipsed structure. Further rotation by 60 degrees is going to give 180 degrees in total. And here we are again going to end up with the staggered structure. Further rotation by 60 degrees, it's going to make it 240 degrees. And we are going to end up with the same eclipsed structure. Again, further rotation by 60 degrees. And we shall be getting it again, the staggered structure. And any further rotation would make it 360 degrees. and that would make 360 degrees. Here it is 300 degrees, 360 degrees, and we are going to get it as the. Here we end up with again the eclipsed structure. So these are the conformers of ethane. So this is what we get, the various structures. Now, as we can very well see that these structures are going to have different repulsion between the various hydrogens. Now, eclipse structure, the hydrogen are going to be the nearest to each other and therefore they are going to repel the most. The eclipse structure would be having the highest energy. If we talk about the staggered structure, its energy would be slightly lower because hydrogen have moved a little further. Here, eclipsed is going to have the same energy. Again, the staggered is going to have a little different energy, lower energy. Here, the eclipse again is going to have the same energy. Staggered is again going to have the same energy, and eclipse is going to have the same energy. When the conformers of ethane move from one to another, that is, they convert from one to another, then in that case, the energy graph goes in this manner. That is, it goes like this. So this is the energy conversion when one conformer of ethane shifts over to another conformer of ethane. If instead of ethane we have propane, then what we are going to find is that propane also undergoes the same kind of energy transformation, energy change. The only difference in the case of propane would be that here we are going to have the CH3 here. It goes CH3 here. This is CH3 here. Here it is CH3, here it is CH3, and here it is CH3, and here it is CH3. As you can very well see, here also we are going to get eclipsed the staggered conformations. But now, when we talk about butane, in case of butane, we find that here we have CH3 and we have CH3. Here we have CH3, here we have CH3. Here again we have CH3, and now here we have CH3. Here we have CH3 and here it is CH3. Here is CH3 and here is CH3. Here is CH3 and here is CH3. Here is CH3 and here is CH3. Now, if you talk about the one structure, it is similar to the seventh structure, but it is not identical to the third structure. In case of ethane and propane, 1, 3, 5, and 7 structures were identical, while 2, 4, and 6 structure were identical. But if we talk about in case of butane, 1 and 7 are identical, 2 and 5, 2 and 6 are identical, 3 and 5 are identical, and fourth one is unique. Now, this particular structure, the first structure is termed in certain books eclipsed, but I prefer to term this particular structure as fully eclipsed. While the second structure is termed as Gotch. The third structure, certain books refer to it as partial eclipsed, or maybe if they talk about fully eclipsed, this structure is termed as eclipsed. I would prefer to call it partially eclipsed. Now, the fourth structure has the lowest energy. It has the alkyl groups the farthest from each other. The lower is the energy of the structure, more stable it becomes. So this particular structure is the most stable one, and this is what we term as the anti-structure. Again, the next structure is partially eclipsed, next structure is Gotch, and the last structure is fully eclipsed. Now, if we talk about the energy, the energy graph of these particular structures, it's quite obvious that fully eclipsed would be having the highest energy. So these two fully eclipsed structures are going to have the highest energy. Gotch is going to have a lower energy as compared to the fully eclipsed structure. So Gotch is going to have a lower energy as compared to the fully eclipsed structure. The partially eclipsed structure is going to have the energy somewhere in between the fully eclipsed and Gotch, while the entire structure would be having the lowest energy. So when butane undergoes the various conformation, it converts from one conformer to another. The energy graph is somewhat a bit different as compared to the energy in case of ethane or propane. So this is the curve that we expect in case of the conformers of butane. This is what we have as the conformers of the aliphatic compounds, the non-cyclic compounds. Now we move on to the cyclic compounds. The simplest cyclic compound we have is called cyclopropane. When we talk about cyclopropane, the structure that we would obtain of cyclopropane by simple geometry is going to be a triangle. Now, if we consider cyclopropane to be a triangle, then in that case, the internal angle should be 60 degrees. But the problem here is that the carbon is sp3 hybridized, and sp3 hybridized carbon is supposed to have an angle of 109 degree 28 minutes or 109.5 degrees. If a particular molecule has the angle by the geometry or the structure different from the angle predicted by hybridization, that molecule is considered to have angle strain. This angle strain is also termed as the Baer strain. The angle strain or the Baer strain. So what I had told you is if a molecule has an angle by the geometry or structure different from the angle predicted by hybridization, this particular molecule has angle strain. Angle strain can actually be put into the numbers. It can be simply calculated by a formula. It is 1 by 2 bracket angle by hybridization minus angle by structure or geometry. So here it is going to be in case of cyclopropane, this angle strain or the Baer strain would turn out to be 1 by 2 divide bracket 109 degree 28 minutes minus 60 degrees. Now, if you know how to deal with the degrees and minutes, you would find that this value turns out to be 24 degrees 44 minutes. Or if you have to deal with decimals only, you can actually consider 109 degree 28 minutes to be 109.5 degrees minus 60 degrees. That will turn out to be 49.5 divided by 2. That turns out to be 24.75 degrees. So that is what we have as the angle strain of cyclopropane. We can even talk about the angle strain of cyclobutane. In case of cyclobutane, the internal angle is actually 90 degrees, should be 90 degrees. So angle strain would turn out to be equal to 1 by 2 bracket 109.5 minus 90 divided by 2. That will turn out to be 19.5 by 2. That turns out to be 9.75 degrees. Now we can talk about cyclopentane. Talking about cyclopentane, the internal angle of cyclopentane is 108 degrees. Now you can find out the internal angle of any polyhedron, a regular polyhedron, by a simple formula. That is, it's equal to 180 minus 360 by n, where n is the number of sides. Okay, so that's how we find out the internal angle. So in case of pentagon, it turns out to be 180 minus 360 by 5. 360 by 5 is 72. So 180 minus 72 is 108 degrees. So here it turns out to be 1 by 2, bracket 109.5 minus 108 is equal to 1.5 divided by 2 is equal to 0.75 degrees. So cyclopentane is practically not having any angle strain. So cyclopentane, the five-membered cyclic structures are quite stable, having the carbon and 10 and sp3 hybridization. Now let's talk about cyclohexane. When we talk about cyclohexane, here the internal angle turns out to be 120 degree, considering it to be planar. So here the angle strain would be 1 by 2 bracket 109.5 minus 120, and that turns out to be minus 10.5 by 2 is equal to minus 5.25 degrees. Now here, please don't consider that if you have a minus angle strain, that means the molecule becomes very stable. Angle strain, whether it be minus or plus, the magnitude matters, not the sign. So here, this particular structure also would be having an angle strain of 5 degree 25, 5.25 degrees. Now here, when we talk about this particular angle strain, please understand that if I lift a particular structure, if I, let us say, if I fold a paper, then in that case, the angle actually decreases from 180 degrees. More I fold the paper, the angle between the planes is going to actually become less. So if instead of planar structure, the cyclohexane were to have a distorted or non-planar structure, then this angle would actually reduce. Rather than cyclohexane to be a planar structure, it becomes a twisted ring structure. Now, this twisted ring structure is termed as a puckered ring structure. The puckered ring structure, by deforming itself, by making itself non-planar, it is able to eliminate the angle strain. And that's why we say that all the structures, all the rings having 6 carbon or more are actually strainless rings. They do not have any strain in them. Now, when we talk about cyclohexane, it is actually existing in certain forms. Now, this particular form which we say, here we talk about this form to be what we call as the chair form. This is what we call as the chair form. If I shift this particular bond a bit up, then in between it will form a structure like this. Now, this structure can be termed as half chair. When the structure moves a little up, further up, then in that case, the structure would convert to this particular structure. Now, this is what we term as the boat structure. But please remember, the cyclohexane doesn't contain only carbon, it contains hydrogen also. And each of the carbon being sp3 hybridized, if the carbon here is here we have the carbon, then the hydrogens will be pointing actually like this. Now, these hydrogens on top, they are termed as flag poles. If we talk about the terminal of the boat, then in that case, the two terminals might be containing two poles for hoisting the flag. So these are termed as flag poles. Due to the flag-pole interaction, or you may simply say FP interaction, the boat structure becomes slightly unstable. The two hydrogens push each other and make the structure a bit twisted. So rather than having a normal boat structure, we end up with a twist boat structure. This is what we call as the twist boat structure. If we call it simply as cyclohexane, then the energy and stability order would turn out to be opposite to each other. And when we talk about the energy and the stability order, we find that it is the chair being the least energy and most stable, followed by twist boat, followed by boat, and the least stable and the most energetic is actually half chair. Now, half chair can also be termed as half boat structure. So these are what we have as conformers of cyclohexane. These also are conformers only.